Okay, let's start the second talk of Professor Stefan Kolb.
Okay, thank you very much. Let me start out by just recalling some notation from yesterday. So we had a symmetrizable Kac-Moody algebra G. The Cartan matrix was indexed by the set I. Then we started out with a Satake diagram or a generalized Satake diagram X tau. And to this, we associated a coideal subalgebra of UQ of G. And so that coideal subalgebra was denoted by BC. And it is generated by three constituents. There was something called MX, which is just UQGX. So the X crucially had to be a finite type, but the I can be any symmetrizable Kac-Moody. Then there was a torus U0 theta. So this was essentially the group algebra of the theta invariants in the root lattice. And then there were these generators BI, which were defined to be Fi minus some coefficient Ci TWX of E tau of I Ki to the -1. And so our quantum symmetric pair coideal subalgebra was generated by these things. And we checked two properties. We checked that it's a coideal, a right coideal, and we indicated y for q equal to 1. If we choose these parameters suitably, we get u of k back. So BC for q equal to 1 goes to u of k if we do this suitably. And then we put a filtration on our algebra. If filtration defined by a degree function, which set the BI equal to 1, and everything in this subalgebra, so we defined H to be MX U0 theta. We said put this in degree 0, the BI is in 1, and then we had a filtration, and we saw that if we then look at the associated gradient of BC, this thing is isomorphic to this algebra A, and A was nothing but U minus times H. Okay, and we call this map phi. And so because we have this isomorphism, and because we can write the algebra A in terms of generators and relations, we essentially also know how to write BC in terms of generators and relations. And I wrote this up quickly at the end of yesterday's talk, but I've written it up again because I forgot one important comment. So what we have here is, well, we have these first two relations, which essentially just tell us how the H commutes with the BI, but then there are these Serre relations, these deformed Serre relations, and we know, and this I didn't say, is that Cij is equal to 0 nearly always, unless I is either so tau of I is either I or it's J. Otherwise, one can show that these things are 0. Okay, so what I want to do today is I want to discuss the star product interpretation of these algebras. We can ask the question, can we somehow determine the relations completely? And the star product interpretation will give us a way to do that. Yeah. And there's a second question one has for UQ of G, the universal R matrix, and an important constituent of that is the so-called quasi-R matrix. And then one asks, is there a similar thing for this coideal subalgebra? And there's a notion of a quasi-K matrix, and one can say what one would like this to satisfy. And the star product interpretation gives us a very easy way to construct this thing. So that's the two things I want to explain today. So what do I mean by a star product? Well, we would like to lift this isomorphism of graded algebras to a isomorphism of filtered vector spaces from BC to A, such that if I go to the graded map, I get phi back. And then, if we have such a thing, then we can perform all our calculations inside A. And we'll see that such an isomorphism exists and that it's possible to describe the algebra structure of BC by some very simple formula. Okay, so to do this lifting, we need what we call the Letzter map. Well, I call this the Letzter map. And that works as follows. So we define a big subalgebra of UQ of G, and I call this U poly. So poly stands for polynomial. And what is this? Well, it's the subalgebra generated by the elements EI, KI to the minus 1, KI to the minus 1, and everything in A. A element A, I not in X. Okay, so that is a big subalgebra of UQG. It's nearly everything. The only thing that's missing are the positive powers of KIs. So we call this poly because it's polynomial in the KIs. That's probably not a good name, but that's what it's now called in the paper. This is a sub-bialgebra of UQG. It's not a Hopf subalgebra. Okay, so then we have a triangular decomposition of UQ of G corresponding to A. It's A, we saw this also yesterday, tensor KQ KI to the plus minus 1 for I in a set which we called I tau. That was a set of representatives of the tau orbits. Tensor the positive nil radical Ix plus. And so whenever we have something here, well, we can reorder. So we can bring all the A stuff to the left. And so if we do this, then we can actually split the A stuff off. Yeah, so we have A plus something else. Now, if we move, and this is why we have this factor EI times KI to the minus 1, yeah, if we move in Fi from the right past this thing, well, then we will only get negative K powers. And so if I move stuff to the left and look what I'm left with, well, then this lies in the ideal, left ideal generated by these two things, maybe with the multiplication by H from the right-hand side. Yeah, so I claim we have a direct sum decomposition into this, and the linear span of EKI to the minus 1 and KI to the minus 1 for I not in X. Okay, and that's not quite, that's certainly not enough. So I may have elements in H. If I bring these to the left-hand side, then I move past here with the adjoint action. So I may have some factors of H on the right and on the left. And moreover, I may have multiples of this, well, anything in the left ideal generated by this. So I can write this like so. So we get a direct sum. So the claim is because of the triangular decomposition of UQ of G, we get a direct sum decomposition like so. Okay, and so what I want to do now is I want to project this onto A. And on the other hand, we see that in the way it's cooked up, here are my generators. So the Fi is a new poly. the E tau of I ki to the -1 is in U poly, and then this TWX, this Lustig operator, just adds stuff in H. So both these summands are in this sub-bialgebra U poly, so I can embed BC into this thing, and the map I want to look at is the composition of this, and I also denote this by psi, and that is the letzte map. Oh. Yes, I'm sorry about that. Yes. So everything, there's only one A, yes. Thank you. Okay. So let's write down some properties of this map. So properties of the letzte map. Well, so I have my filtration on BC, and I have a filtration on A. If I have something in filter degree n, then that means, well, I have at most n of the BIs for I naught in X. Then that means I have at most n of the FIs for I naught in X. And that means I land in filter degree n of the graded algebra A. So the first observation is psi is a linear map of filtered vector spaces. Okay, secondly, or firstly, so that was just a preamble. Well, if I have this psi on a product, A times B, then I can compare this to what I get when I evaluate on A times psi of B. Well, so B minus psi of B is in the kernel of my projection, and the kernel is a left ideal. So then these two things have to coincide. So that is true for all A, B in BC. And then this projection map psi is H bilinear. Again, that follows from the way it's defined. So psi of H1 B H2 is H1 psi of B H2 for all B and BC, H1, H2, and H. And then I can ask, well, okay, so I have this filtered map. What is the associated graded map? And by the way it is defined, the associated graded is exactly our phi. I mean, what do I do if I take something in filter degree n, which involves n of these BIs? Then all of the corresponding FIs have to survive. Otherwise, I would go to 0. So I can replace anywhere in a polynomial in these generators the BIs by the FIs. And that was how we had defined this map phi earlier on. Yeah, so the graded of psi is phi. And then finally, if I put these things together, well, then I see that psi of A times B is equal to psi of A times psi of B. Yeah, the phi was an algebra homomorphism. So up to something of lower order, plus lower order terms, the psi is also an algebra homomorphism. Okay, so that is the letzte map. And now we can use the letzte map to define our star product on the algebra A. So we will just lift the algebra structure of BC to the algebra A. So we define psi of A, psi of B. Yes, so I call both of the maps psi. So then I can go from here to there. Is that the question? A times psi of B in number one happens here. And then I go down. Okay. So we define our star by just pulling back the algebra structure from BC. So we take psi to the minus 1 of A, psi to the minus 1 of B. Yeah, then we're in BC. We multiply them in BC, and then we push them back to psi. So that's for all A, B, in A. And this gives us an associative algebra structure because we've just used the linear isomorphism to pull the algebra structure of B onto A. So note the following. Our algebra A is an N0 graded algebra generated in degree 0 and 1. So the generators Fi for I naught and X, they sit in degree 1. And so now we have this new product on this algebra A. Let's list some properties of this new product. So first one I said already. So star is an associative bilinear algebra structure. Is an associative algebra structure. Secondly, by what we've observed upstairs, so if I form A star B, well, that is by this formula down here. If I plug in A star B, so psi of this product is just psi on each of the factors plus lower order terms. Yeah, so this is A times B plus lower order terms. Then thirdly, if I multiply by something in H, then it's just the usual multiplication. So this is for all H and H and A and A. Okay, and something which satisfies these three properties, I call, because A0 is H. Yeah, so I have an A0 equivariant. So I call this a zero equivariant star product on the N0 graded algebra A. And now the question is, if we want to describe something like that, how do we do this? Well, because my algebra is generated in degree 0 and 1, I really only need to know how to multiply by elements in degree 1. Yeah, and so the star product algebra will also be generated in degree 0 and 1. So we have our A. We can split off the degree 0 part. So we have this as a tensor product of H tensor this negative nil radical r minus x. I mean, this is here a special instance of a Radford byproduct. Here we have this Hopf subalgebra. If I take the whole parabolic, then I have a Hopf algebra and I have a Hopf subalgebra, and I have a projection onto this Hopf subalgebra just by sending the FIs for I naught and x to 0. And that's a Hopf algebra homomorphism. And then I can look at some kind of coinvariance, and that is this thing. And Radford says, well, this is a very general setting, and somehow this is a Jeter-Drinfeld module over that, and you can form a smash product. And we don't need that, but this is what's happening here. And we can stare at this Rx minus, and we can make it more explicit. So Rx minus is U minus intersect TWX of U minus in this case. Okay, so if we want to describe our star product, then all we need to know is how do we multiply by degree 1 elements, from the left. So how do I well, we know how to multiply by h because that's just the normal multiplication. So we need to know how to multiply something in Rx minus by an arbitrary degree 1 element. Yeah, so we need to know what is f star u for all f of degree 1. So this in Rx minus of degree 1, and u in Rx minus. Okay. And this we can actually calculate. So let's assume for simplicity, that X is the empty set. It makes our calculation easier. Okay. So then our H is just the subalgebra generated by these Ki, K tau of I. So the diagram automorphism need not be the identity. And the Rx minus, I mean, the TWX of U minus is just U minus. So this is U minus. And so then we need to know, it's unreadable now, but we need to know what is Fi star U for any element in U minus. Okay, so let's calculate this. So let's take an element U in U minus. We can write this as psi of B, U minus for some B and BC. Then we have, so what I want to know is what is Fi star U, and that is just a little instructive calculation. So we take our definition is up there. So I have to take psi of the preimage. Well, the preimage of Fi under the Letzter map is just the Bi. And then U was psi of B. So I can just write B here. But then we saw by the property I have arrays that we can replace the B here by psi of B. So this is psi of Bi, and I plug in what Bi is. Bi is Fi minus Ci e tau of I Ki to the minus 1. And psi of b is u, so I can write u like so. So that is what this is. And then, well, I look at the first term, yeah, I get psi of fi times u. Well, that is undramatic. That'll be just fiu, and then I get minus ci psi of, okay, so I bring the ki to the right-hand side to be able to apply my psi. So I get a factor q to the alpha tau of I, psi of, then the ki, sorry, I bring it to the left, is here. Then I have an e tau of I and a u. And because I know that everything that has an e on the right-hand side goes to 0, I can change this product to a commutator. And then this is still correct. And now this commutator, the u is in u minus, so I know how to deal with that. There are these formulas, so ei u commutator is, we need these Lustig or Kashiwara derivations. So this is ki dil of u minus dir of u ki to the minus 1 divided by qi minus qi to the minus 1. And we see that if we evaluate the psi, right, the psi will send negative k powers to 0. And I already have, I get here a k tau of I and a k tau of I to the minus 1. And I already have a ki to the minus 1. So this term here will go to 0. And the only thing I'm left with is this term for I replaced by tau of I. Yeah, so what do we get? We get that this is fi times u, because this is already in u minus, minus ci. Then we have a q of alpha I, alpha tau of I, divided, that comes from up here, by qi minus qi to the minus 1. Then this term up here survives, with I replaced by tau of I, so I get k I to the minus 1, k tau of I, times this Lustig Kashiwara skew derivative delta tau of I L evaluated on u. Now this will be in u minus, and so if I then apply psi to it, well, this already is in A. So there's the formula, and that was the calculation. A little comment: if we do this in general for non-empty x, then it doesn't change by much. Or do I have colored chalk? Maybe I have here, no?
We have yellow.
Oh, yellow is great. Sorry, I didn't dare to open this. Okay, so if x is not empty, then all that happens is I need to put a wx here, longest element with respect to x. I need to replace this by k minus alpha I plus wx alpha tau of I. Yeah, so basically I have to apply wx here, and I have to conjugate by twx and twx to the minus 1. And if the definition of Rx minus is still up there, so this works. If u is in Rx minus, then this is okay, because I can apply twx to the minus 1. then I'm in U minus, then I can differentiate, I'm still in U minus, and then I apply the TWX again. Then I may no longer be in U minus, but that doesn't matter. Okay, so that's the general formula. And the point is that this formula contains all the information of the algebra BC. Yeah, so, well, in the case where X is the empty set, in the general case, I fortunately can't see this anymore. I have to do this not only for Fi, but for everything in degree 1 of Rx. Now, Rx looks like that. And in general, Rx1 is the span of right adjoint action of H on the Fi for I not in X. Okay, so I have to calculate more if I want to do this in general. I need to have these formulas for all right adjoint action of H on it. Yeah, and this I haven't written down. Okay. So this formula we can now use to determine these lower order terms. So that's what I want to explain next. So as an example, let's look at the case. So let's look at this relation here, Sij of B of I, Bj is equal to Cij. In the case I is equal to tau of j. So I said I only have to look at these two cases, or tau of I is equal to j, for X equal the empty set. One can do this in general, only the calculation will get longer, and that's maybe not so important. So what is the idea? Well, we have the Serre polynomial, and so the point is we can now calculate in the space A. But in the space A, or in the algebra A, we already have something which is 0. So we have Sij of Fi, Fj. We know that this is 0. So the Serre polynomial of Fi and j, that's just the usual quantum Serre relation. That is 0. Now, we have here a mechanism which allows us to translate usual multiplication into the star multiplication. So what we do is we just rewrite our usual formulas here in terms of the star multiplication, and then, well, we get something which is 0. Yeah. So we write this in terms of star. Yeah, and then because A star, yeah, so the space A with star is isomorphic to BC, that's how we've cooked it up. Well, then I get my relation in, my defining relation in BC. Okay, we need a little bit properties of this skew derivation. So delta IL is a skew derivation, that's what we need. Of A times B is delta IL of A times B plus Q to the alpha I mu A delta IL B if A is in U minus mu. That's one thing we need. And so the other thing, well, then you use this to evaluate what is delta IL of Fi to the power n. Well, and you get some Q factor. So it turns out this is n Qi squared times Fi to the n minus 1, where this is the non-symmetric Q number, 1 minus p to the n divided by 1 minus p. Okay, and with this we can now calculate. So we split up our Serre polynomials, and we want to rewrite Fi to the m, Fj, Fi to the n in terms of the star product. And then we sum these things up with the binomial coefficients and so on. So first thing, if we have Fi star power to the n, yeah, so that's Fi star, Fi star, Fi n times. Well, this I can easily evaluate. The point is I have this formula here. Yeah, I multiply Fi by itself, but then all that happens is I need to take the derivative with respect to tau of I, but tau of I is not I, so that's our assumption here. Tau of I is j, and therefore this is just the usual multiplication. Okay, so that already deals with this term. Then I calculate Fj star Fi to the n, plug this into my formula. So I get Fj Fi minus Ci Q to the alpha I, alpha tau of I, and then get a Ki to the minus 1 K tau of I. And then I take the derivative with respect to tau of I, tau of j, which is I. So we get an n Qi squared Fi to the n minus 1. And I may want to bring these terms to the very right-hand side so that I can apply my skew derivatives again, or my star product. So we get Fj Fi minus Ci. Now, if I commute this past, I get a Qi to the 2n minus minus 2n minus 1. And then I have to, this is a plus. And then I have to move this one past, and this gives me a something. So I took Fj. Yeah, so I've written this differently, right? So the Fj, so the minus here was wrong. So the minus goes there, and then I get a minus sign here. And I get an n times aij, like so. And then I have the n Qi squared Fi to the n minus 1 times Ki K tau of I to the minus 1. So that is one star product. And now I continue. So now we have an I again, Fi star Fj Fi to the n. And this I can also calculate. So it's the normal product Fi Fj Fi to the n minus, yeah, so this was a j, this was a j, minus Ci, again, this formula, qi minus qi to the minus 1, q to the alpha I, alpha j, and then I have a ki to the minus 1, kj, and I want to move them to the other side. So then I get an fi to the n, because this j here gets eaten up. And now I move my ki to the minus 1 past this. So I get a 2n qi to the 2n minus, and from the k tau of I get a n minus 1, I get an n minus 1 times aij, together with the plus 1, which was there already previously. Okay, so that's what I get, and then I get a k tau of I, or j ki to the minus 1. And so then I can reiterate this, and I can do this m times. And what happens then is, well, I just get the m here, and I get here, so this n is n minus 1 plus 1, and in general, I get n plus m minus 1, like so. I hope I've done this correctly. And so now we put everything together. Yeah, so now I have my formula for fi to the m, fj, fi to the n. I to the n. And that is what I want. Well, I plug this formula in to, so this expression I plug in here, and then I get this. So I get the star product, fi star m star fj star fi star n. And then I get two error terms, namely the one I have here and the one I have there, multiplied by fi star to the m. Yeah, so I get two error terms, and maybe I abbreviate this a little bit. So I get something that depends, some alpha which depends on m n ij times f to the m plus n minus 1 times k j ki to the minus 1. And I get a plus beta with a similar argument, f to the m plus n minus 1, k I kj to the minus 1. Yeah, and so now we sum up the left-hand side, and well, then the right-hand side will also be 0. And if I keep track of my coefficients, then I get an explicit formula. Yeah, so the formula we get, yeah, so we obtain that Sij of Bi Bj is equal to, okay, I have thrown out my coefficients, but there is an alpha ij times f to the m. So what is now m and n? In my Serre relation, the m is always 1 minus aij minus l, and the n is l. So m plus n minus 1 is minus aij times kj ki to the minus 1 plus some beta ij f to the minus aij ki kj to the minus 1. Yeah, and so in this way I can prove these, I can obtain these defining relations for my quantum symmetric pair coideal subalgebra. And so this has been done. So just as a remark, so this is joint work with Milin Yakimov. And what happens, so we have dealt here with the case where tau of I is j. So the question is, what happens in the case when tau of I is I? And in this case, one gets relations which look very pretty. So one gets the Serre polynomial, and all one has to do is one has to replace so in the usual Serre relation, we have f, we have x to the 1 minus aij minus l. Well, there's a family of orthogonal polynomials, h, and one gets, so these are the continuous Q-Hermite polynomials, and one just gets those if one does this. And so this is a very classical family of orthogonal polynomials. And this is 0 if I is, if j is not in X. Now, if j is in X, then this is something which can also be expressed in terms of orthogonal polynomials. And these are so-called Q-Polacek polynomials, which have been, I found this out last summer, they have been investigated by Murad Ismail about 35 years ago. He had forgotten about this, but his collaborator, Dennis Stanton, reminded him. So one gets something non-zero here. Okay, so this is interesting because there are other ways to write these defining relations. Yeah, Wei-Chiang Wang and his collaborators have very nice ways. They get something which structurally looks the same, but instead of these continuous Q-Hermite polynomials, they get what they call I divided powers. So one can replace by I divided powers. The I divided powers are nicer in some way. These are also some polynomials which are recursively defined because they're integral. And these things need some reparametrization, which makes them non-integral. Okay, but so what I wanted to say is with the star product interpretation, one can get all the defining relations. Yeah, one can write out all these relations here explicitly, and that was still missing from the general theory, in particular in the Kac-Moody case. Okay, the second thing what the star product is good for is to give us this quasi-K matrix. So if we look at UQG, then, so just quick reminder, so we have the bar involution of UQG to itself, yeah, which sends EI to itself, but KI to its inverse, and crucially, Q to the minus 1, and Fi to itself. So this can be used to describe the quasi-R matrix. So for UQG, we have the quasi-R matrix. This is capital theta. We saw this already yesterday. So this is an element in, well, it's an infinite sum of elements in U minus tensor U plus. Yeah, and formally, I may want to write this as some mu and q. Maybe I need a sign, some e mu's, some f mu's, tensor some e mu's. But crucially, this has a second description if one has this this bar involution. Namely, one can do the following. We can take an arbitrary element. We can look at the diagonal delta of UQG and in a way define two involutions on that. On the one hand, we can, take delta u, so send delta of u to delta of u bar. On the other hand, we can look at bar tensor bar of delta of u. And so then this quasi-R matrix intertwines between these two elements for all u. And once one has this quasi-R matrix, one can build a universal R matrix just by multiplying by a Cartan part. Yeah, I mean, this is due to the fact that UQG is essentially a quantum double. So we have the universal R is something like the quasi-R composed with some Cartan part, kappa minus, which only depends on weight spaces. Okay, and so now we want to do something similar for BC. And so here we want the quasi-K matrix. K matrix. And so this was formulated. So we have three things we want to do. So so this is an element. I write theta prime or theta I if you want. So this is an element in Q plus. I replace the U minus by BC, tensor U plus mu. And so Huanchen Bao and Wei-Chiang Wang in 2013, and then published, it was in 2018, wrote down this extremely beautiful formula, which is an analog of this. They said, well, we'd like this thing to intertwine between delta of B bar. Okay, so we want a bar involution on BC, which is, I call this delta B, which satisfies delta B of BI is BI, and delta B restricted to this subalgebra H is just the usual bar involution restricted to H. So I want to look at this, and on the other hand, I can look at delta B for B in BC. And because it's a co-ideal, this lies in B tensor U, so I can apply bar B tensor usual bar to this. And I would like an intertwiner between these two things, and that is what this thing is supposed to be. Theta I. Theta I. Okay, and so one could ask, what happens here? Can we give a description which is analogous to this? And one can also ask, but that's maybe for tomorrow, what would one put here? Okay, and the answer is, at least in the case where X is the empty set, surprisingly simple. So what we do is we take, we have our Letzter map, and the Letzter map goes from BC to U minus. Okay, so if we have this theta here in U minus tensor U plus, then we can just pull back the first tensor factor by the using the Letzter map. And then we'll get something which at least lies in the right space. So we define. So this works for, well, we can define this always. We define this to be psi to the -1 tensor identity of theta. And then the theorem is a proposition so this is again with Milan-Yakimov that this is a good element. So, but unfortunately, we can only prove this if X is the empty set so far. So we want this intertwiner relation. Well, we only have to check this on the generators. So we have delta of BI. Yeah, BI is its own bar, so no need to write the bar there. Multiplied by this pulled back quasi R matrix is indeed, it looks like this, BI tensor Ki, that's very good, minus C tau of I Q to the alpha I, alpha tau of I, K tau of I to the -1 Ki tensor E tau of I Ki plus 1 tensor F. I should have put this 1 tensor Fi. Okay, so now if you and delta H theta I is theta I delta H for all H in U0 theta. Okay, and that's all of H really in the case where X is the empty set. Yeah, so now we want to compare this. Does this do what we want? And yes, it does. So what would we like on the right-hand side? Well, we have to recall what is delta of BI. In this case, it's BI tensor Ki to the -1 plus 1 tensor Fi. And then we get this, well, we have the, right, we calculated this yesterday, essentially, when we checked the coideal property. So we have Ci K tau of I times Ki to the -1 tensor E tau of I Ki to the -1. Now, if I want to bar this, I want to apply bar B tensor bar U to this, then this Ki to the -1 becomes a Ki. Here nothing happens. I have to bar the Ci. This thing becomes its inverse. And here the Ki becomes a Ki to the -1 becomes a Ki. Then I see, oh yes, it looks like that, with the only condition that these two factors need to be the same. I need Ci bar is C tau of I Q to the alpha I alpha tau of I. Okay, if I have this, then this thing is bar involution. Then this thing satisfies these properties. And it turns out, and one can use this formula to prove it, that this is actually the condition under which such a bar involution exists. Okay. In the last 20 seconds, so now how do we use star products to prove this? Well, we use the formula on the left-hand side, this one in the middle there, and we just rewrite it in terms of the star product. And then after we've done this, we replace the Fi's by the Bi's everywhere, and then we end up here. And that's a very much shorter proof to obtain this quasi K matrix than what was done previously. I was hoping to calculate this for X, not empty set, before I came here, but I was snowed under. Okay, and my time is up by 20 seconds, so I'm sorry, and thank you very much.
Any question or comment?
So you listed a series of properties for the map psi at the beginning of the lecture. I was wondering how many such, if you knew about how many such functions with those properties existed, and if they would define different versions of the star operation.
That is a very good question. So I don't know how many exist. But it is certainly true that there is no statement that this is unique, right? All I need is a graded isomorphism of vector spaces, or a filtered isomorphism of vector spaces, such that the associated graded map is the map I originally started with. And it may well be that, so here we've cooked this up very carefully, and we've stared at this for a long time before we decided that this is how we want to define our psi. In the case when X is not the empty set, we haven't stared, and maybe one of the reasons why I can't prove it, or not as easily, is that I've taken the wrong map. That may well be. Yeah, so it's a quantization problem, if you want, or from graded to filtered. And so we haven't thought about the obstruction and how many there are. But that's certainly a good question.
Thank you.
Other question or comment? No? Then let's thank the speaker again.